BKW Physics. I'm Mr. McConley, and today we're going to talk about the Bohr model, energy level transitions. But before I start that, I want to remind you that previous we talked about this idea where it was a model for thinking where Eddie the electron was trapped down in a hole, and he gained energy equals HF from photons of light. That got him excited if it was at the threshold frequency. He got excited enough that he overcame, or he got to the level of the work function, and then he would escape as a photoelectron, and we had a way to figure out the energy in that case. Okay. That being said, how does this tie back to the Bohr model? Well, remember Bohr laid it out like this. He said, well, you got a nucleus, and around the nucleus, there's electrons that are in various orbitals or shells. Now, what did he say about the levels? What did he call the level or the shell that was closest to the nucleus? What's that name for that? Ground. Ground state. And how about if you go way out here, and this is the electron that is just going to basically take off in a second because it's very loosely attached. What is it called when that electron says goodbye and leaves? These are all excited states out here, and specifically when you get out to the end, they call it ionization. Does that ring a bell? Yeah. So ionization, when the electron really is able to leave. So this is the way Bohr spelled it out, and you can kind of see this or tie the two together in your mind. So this situation right here applies to jumping energy levels, right? And you're getting some incoming energy, which is causing some excitement and then causing some visible light to be emitted. Okay, so try to tie the two together in your mind. Thinking of that, if we are talking about these energy levels here, and say we're going from in a hydrogen, I'm just looking at this one page from your physics reference table. If I'm in hydrogen and I'm going from like a level 5, which they call N5, and I'm jumping down to an N2, I'm getting closer to the ground state. I'm going this way, okay? I'm jumping levels, getting closer to the nucleus. If I'm doing that, then there's going to be energy, right? Because these, you can see on the right, are various amounts of energy, and they're all written as negatives. Why are they written as negatives again? Why would that be?
Because you're getting closer to the...
So as you get closer, the numbers are bigger negatives. Why would that be? What's going on there? More energy to get the electron to be released or ionized. Okay? So when you get right up here to the ionization level, it doesn't take anything, you know. When we were scraping back with static electricity, when we were scraping electrons off of the fur, it's because we were scraping the ones that were up here. They were almost ready to go anyway. They weren't really attached by that much energy. You just physically can wipe them right off. It would be really hard to scrape electrons off that are in the ground state. Okay? That's very difficult. All right. So what's the equation that spells out the energy that it's going to take to do these transitions? Well, it's a simple equation. You'll find it in your reference table, and I can scroll ahead a few pages here and show you where it's at. Oh, I think I already missed it. Modern, there it is. Okay, so it says you write it exactly as they write it. The energy of a photon is equal to the energy initial minus the energy final. This one right here, you can't read it on the video. And what's going on here is you're looking at the two energy levels, and you're just basically subtracting the numbers. And you got to be a little careful, because if, for instance, we're talking about, let's do an example. Let's go hydrogen. This is the, back up hydrogen energy level diagram is on the left. If we're doing hydrogen and we're going from N6, hydrogen, and we're going from N6 to N3. N6 to N3. Let's just do the subtraction. And I want you to note that there's negatives there, so be careful. So we're going to take these numbers. What's the N6? It's a negative 0.38. What are the units on that? They're EVs, electron volts. And then we're going to subtract, and we're jumping down to the 3, which is a negative 1.51 electron volts. So get out your handy dandy calculator and tell me what that gives you. How much energy is that photon? How much energy are we talking about here? What do you got?
1.13.
1.13. I'll assume he's right because I didn't do the math. But since this is a double negative, right? It should make this a positive. This should be bigger. It sounds about right when I'm looking at your numbers. Seems about right. And then what you could do further is that electron volts aren't always that useful. In fact, they're not very useful at all in terms of plugging it into the equation. So now you could convert this to joules. How would you go about doing that? Well, if you look on the first page of your reference table, you will notice that electron volts can be converted to joules. Let's scroll there and see what we're talking about here. It says, where does it say it? 1 electron volt is equal to 1.6 e negative 19 joules. So I could do 1.6 e negative 19 and convert that to joules. Why would I want to do that though? What's the point? Why go through the hassle? I guess is what I'm saying. Well, here's the reason. Normally, you're doing these transitions so that you can find something else. And usually the other thing you're trying to find is something like the frequency. So if you were looking for the frequency, you might first have to do a subtraction to get the energy. So say I do the subtraction to get the energy, now do you think that I can just take that number, that 1.13 electron volts, and plug it right in there? The answer is you cannot, because this has to be in joules. So the reason you might have to do a conversion is because you might have to take your electron volts, make them into joules so that you can eventually find the frequency. Does that make sense? Furthermore, there's another equation that's tied right in, and since we're talking about it, let's do it. You have E equals HF. But I want you to recall from not so long ago, from the light chapter when we talked about light and waves, that velocity was frequency times wavelength. Do you recall that? Very common equation that we used a lot. Well, now that we're talking about, now we're into energy, we're talking energy of electrons, and electrons give off visible light, this equation comes into play again. Okay? And the way it comes into play is that you can rearrange this, making it velocity of the wavelength, and then plug it right in there. And so our new equation becomes energy is h, but instead of f, it's v over lambda. Now I could call it good, but your reference table takes it one step further. They, instead of calling that a v, they call it the letter c. And what does c mean? It's the speed of light, right? It's the speed of light. Celeritas. So they write it this way, hc over lambda. That is another equation in your reference table under modern physics that ties the two things together. The reason we can plug in this v equals f lambda is what? Why? It's giving off light. Okay? So then you tie it into waves, and then you can kind of combine these two things and come up with this. Okay? So we got equation from the other day, newer equation, another new equation just to get the energy level. This is a very easy one to use. You just subtract. I mean, you know, at this point in the year, it's like, okay. I think we're getting kind of long in the video, so I'm going to end this video, and I'm going to do another short video where I'm going to show you an example of how we could run this through.